Hello, welcome to subscribe to the last episode for this year. I don't even know where the time went, and you will have noticed that I didn't know where the time went because the last episode was 30th of October. It's now December 12th, which means I didn't do an episode for 6 weeks, so I'm really sorry for this. This is episode number 8 of the Device to Cloud series, and today I'm going to do what I should have done already 5 weeks ago, and that is I'm going to show you the internals of the little Raspberry Pi that lives in my car. So we're going to take a look into the device and what's running on it. It's an embedded Linux, runs Raspbian, and so we're going to take a look at the code. The code is up on GitHub, and also the startup scripts and stuff is on GitHub. So I'm going to walk you through what's actually on the device, and what you'll notice is that the code is a little bit of a very large main function, so not necessarily cleaned up, and that is because I really want to get to in the quickest way to get some data, collect some data out of the car and get that out. So I took an existing project, adapted that project to my needs. So I took a project called OBDII GPS Logger, which is GPL licensed, and extended it. So the result of that obviously sits in my personal repository. It's not Microsoft software, and that is a fork of that, and that's also then GPS licensed. So if you're worried about this, then you should take note of that fact. So let me go and switch over to the screen capture, and then we're going to take a look at the Pi per se, and then also we're going to go and move on to GitHub, and then I'm going to show you the code, and I'm going to walk you through all the necessary pieces. The Pi that usually lives in my car is connected to my PC now, and it's sitting on the same network, so I can go and log in. And that's where it's on there. So I'm logging in from my main PC here. And what this little computer has been doing is, and I showed this in Table Explorer, has been logging faithfully a bunch of trips. As you can see, this is September and November and October and December. So it's been kind of on a day-by-day basis, has been logging my trips. And it's been logging the temperature and the RPMs, and I think an airflow measure. I'm not going to get back to this. I showed you in the previous episode how I can plot graphs about this in Excel. How would you get that data into Excel in case you ask, or if you wonder? Because I'm using here this Table Explorer tool. What you need to do is you need to get the newest Power Query tool, the Power Query Preview, and that actually has a way for you to import from the Azure table storage if you are putting data into the table storage as I do. So the very newest version of the Power Query Preview for Excel allows you to do this. And then once you have that, then it's obviously very easy to plot graphs in Excel. So let's go back to the Pi. What I have on the Pi, the way I set up that Pi is I built most of the components here on the Pi. So if I go to the Git repository, there are two projects. There is the OBDII GPS Logger, and there's Cupid Proton. Cupid Proton is the AMQP client that's built by the Apache project, and OBDII GPS Logger is a fork that I created of another project. So we're going to go and take a look at the browser here and see what those things are. So Cupid Proton is a high-performance lightweight messaging library. It's built as a cross-platform library, and it is the library that we are recommending. Listen to that again. That we are recommending from Microsoft for speaking with Windows Azure Service Bus from platforms and languages that are not C#, .NET. Or .NET languages per se, so including Visual Basic. So if you're using C, if you're using PHP, if you're using Python, then Cupid Proton, and if you're using Java, then Cupid Proton is the best messaging client because we're directly contributing to that project and we're helping with that project. And so that's what we like. If you want to go and build this yourself, you can go and obviously go to the source code here, which sits in the source code repository, the SVN repository of Apache. And if you want to use Git, so if you want to go and basically just grab this with Git, you can go to GitHub, where the repository is being mirrored. So you can go to Apache Qpid Proton on GitHub, and that's where the Proton repository lives. And there are also instructions for how to go and build it. So this is what lives on the Pi here. So if I go and list that up, you'll find that I pulled the version. You need to be a little careful that you actually pull the 0.5 version. As of just when I built this up, and the last Qpid Proton version that was in the distribution for Raspbian was an earlier version of Qpid Proton. You really want to have the newest version. You want to build from source with Qpid Proton, because there's a lot of activity in the project and you want to get the latest bits, because we and the Proton Qpid projects were working very actively to improve performance and get rid of some bugs. And here you have the Proton C and you have the Proton J library. And the Proton J library is obviously the one for Java. So I'm building this on the Pi. I'm not going to show you any of the build process. You basically just go and read the documentation, but it's a standard process for Linux, for building things on Linux. You go and get the repository, make a build directory, run CMake. If you don't have CMake yet, you have to go and get CMake, obviously, and then go and build it. And they can go and say build install, and it drops the libraries into the libraries directory on your machine. The other project, as I said, is the OBDII GPS logger project. That is a version of this wonderful thing here. So this Chunky at iculus.org that has built this wonderful tool set that will go and grab data from an OBDII device. I showed you that in the last episode. I'm sitting in my car. I have a USB wired version because, frankly, I didn't get the Bluetooth connectivity between I have two Bluetooth dongles, and I couldn't get that to work. So I took a USB version of the Elm 327, and he's got some funky stuff he can go and do with his tool. I am effectively taking the core logger project that is being created, and I no longer log to the database, but I rewrote it in my own fork to log to Windows Azure. So this is the fork. Sits in my repository, Clemens V, D2C RPI OBD logger. Again, this is now GPL licensed because I am building on someone else's code that is GPL licensed, and so just be mindful of that when you pull this. And in the source, there's still the exact repository as I found it. I basically just forked that off the SVN repository of this project. And then I added the Azure logger. So otherwise the project is intact. I just added my own logger here. And that's a riff of the original logger, basically evacuated most of those things. And you will find, as I show that to you in a moment, that it's probably not the cleanest of all codes, but and certainly is one fat, big main function. But the goal here is not to make it too structured, not to factor it nicely, but actually to have it all in one place so I can go and show it to you easily how we can go and do this. Before I go and show you the code, let me show the startup script. The startup script I have here in a gist. So if you go and look up in my gists on GitHub, Clemens V, Azure OBD, you will find the startup script. And so the assumption here is the following. I have the Pi is configured to live in my car. And in my car, the Pi is connected using a wireless hub. And the wireless hub is being provided by the car per se. Now, as the wireless, and you can obviously, not everybody has the luxury of having a wireless hub built in straight into their car. So if you don't, you can obviously use a phone and use that as a wireless hub with internet sharing. As the Pi boots up, and the wireless LAN may not yet be available. There's a kind of a race condition that I have when the Pi boots up, and that's racing with the car's systems booting up. So sometimes it may happen that the wireless LAN connection cannot be established, and that's an asynchronous thing. So as this starts up, what I'm doing is I'm effectively waiting here. I'm doing this retry count, and I'm waiting until I can ping the Google DNS service, which is a pretty, this allows pings, so that's one good thing. And then it usually can be seen everywhere. And so I'm waiting until I can actually ping Google, and wait until I exhaust the retries. And only if I have a network connection to the outer world, then I'm actually going to start the Azure OBD. The reason why I'm pinging Google, not us, is that we don't respond to pings. And so then I go and start the OBD logger here, and I'm pulling the data. This is the source here. I'm pulling from TTY USB 0, so that's where the OBD logger is, or the Elm 327 is connected. I'm setting the baud rate to 38400, and then I'm setting the queue address, and this all goes in one expression. And this is where you would have to go and edit this. You set the key. So I'm assuming that you use the owner. You may be using another issuer name in Service Bus. The owner's key, the namespace name, and then you specify the name of the queue you want to get the data through, or the topic, right here. So the credentials plus the queue name are all expressed in one go in the AMQP address, and AMQP stands for this running over SSL. And then I'm basically starting this, and this keeps going until the until the program terminates, which is never, in fact. And so this just keeps going. So the goal of this script here, this script lives in, as you can see, in init, and that starts up automatically. I mark this for automatic execution, and then this gets executed and gets run when the little machine starts. So, and that's its only purpose, is to run this script, basically to go and automatically connect to the wireless network in the car, and then go and run this script and then log the trip. So logging the trip, let's go into the actual project that's in the Azure logger. If I go to the main file, this is where kind of most of the action happens. Let's go, and before I go into the details, let's go quickly back and see what we can actually log. So that's in source and OBD info, and the OBD service commands are listed here. This is kind of what you can get out of the car. So you can specify this on the command line, what kind of data you want to go and log. The default is that it logs the temperature, and that it logs the RPMs, the speed, and the airflow rate from the airflow sensor. So that's kind of what you see reflected in the telemetry table. If I go and get it here, so temperature, RPM, VSS, MAF, and that's what's being put into the messages. You can add that on the command line. You can add some of these other readings here. The more you read, because it's a serial port polling mechanism, effectively, that goes and gets every second gets a new record, and it's not very fast with 38400. You will not be able to go and get all of this data, even if you wanted to. So you need to be a little selective about what you want, and not all the cars are actually returning all the data. So this is also something that depends on your car, but these 4 values are pretty reliably available from all cars that are supporting this. And then there's a number of proprietary ones that vary from model to model. So let's go back. So these are kind of the values, the values you can go and specify. There's also a way to specify the defaults. And so here's the here's the core program. Let me just make this a little bit bigger. So Gary Briggs originally wrote this thing, and I'm just using this so the GPL still applies, and I just did a riff of that original project. So the and what you'll find is that it's also the core handling of the OBD device is very similar. So I'm going to point out the things that are a little special. So first of all, I'm generating a drive ID. I'm generating a new drive. So every drive has its own UUID, so I can go and log when I started driving. So the assumption is that as for every time the device starts, that is a drive, because the device hangs on the power supply of the car. Obviously, it sits on the cigarette lighter port, so it turns off automatically when the device when the car stops. And so as I start up, I'm simply assuming we have a new drive here. This is how I collect the parameters, and how we can get the collect the baud rate and collect the queue address. This is something that you saw in the startup script. These are the columns to log. So that's a comma separate list of the log of the columns. And now I'm setting up the serial board. I'm checking the queue address, and then you can also show what the capabilities are. So this is how you can find out what your car speaks. So the show capabilities option allows you to kind of dump when you have this connected to your car, seeing what your car emits, and then you can go and select it. And it also supports GPS, even though I don't have GPS plumbed on my Pi specifically. So I have no GPS support in my data. Now it goes through and checks what the total commands are. So this is mostly all standard stuff. And now I go and this is where the beef starts here. So that's line 380. Where I'm going to go and create and initialize the messenger class. And this is where I'm starting interacting with Qpid Proton. So I'm creating the messenger. The messenger is the library that is talking to AMQP with the service bus. And I'm starting it up. And I'm creating a message. The addressing in Proton is that I'm addressing every individual message. So I'm setting the queue address. The queue address is what we said here in the start script with the owner, the key, the namespace, and the queue name. So that's how that flows. This is the /q argument that I showed you earlier. And then this is the trip message. So we have two kinds of messages. We have a telemetry message, tele, and we have a trip message, trip. And I'm going to open up I'm creating the message body here. I'm entering into the body. I'm creating a map, which is a dictionary. I'm entering the map. I'm now setting the key, which is ID. And I'm then setting the UUID, which is the drive ID. Exit the map, exit the body. Put the message into the messenger. And then check whether that was sent. And once that was sent, I go and free the message. So this is now kind of flushed out to the other side, to the receiver. This now went to service bus and says, and announced effectively that we have just started a new drive. And now I go into the loop, and this is the non-terminating loop. If I don't have a message yet in that iteration, I'm creating a new one, set the address, make a telemetry message, and then I start opening up the messaging body, create the body, enter into it, create a map at the root, enter into the root, set the drive ID, and then set the header. And in the header section, I put a list. So now I put the list of all the telemetry column headers into this. I start with the datetime. And now I'm adding all the supported OBD commands, so all the commands that we selected. So by default, this would be temperature and RPM and VSS and MAF. If I have GPS, which I don't, then I'm going to add all the GPS parameters, latitude, longitude, altitude, course, speed, and the time. And now I'm exiting out of the list. And now in the map, so now we have in that map, we have a header with the columns, and now I'm opening up the body, the data section, and now I'm going to put another list, and this is going to be a list of lists where all the telemetry rows are going to go. So this is the preparation of the message per se. And now I am going to get the time. I'm going to start the list for a particular row of telemetry data row. I'm going to go into this. I'm going to put the time as a double value, and and this is kind of pulling from the ODB device, pulling the individual values one by one. So it's going to the OBD device. This is the get OBD value that's communicating with the device, grabs the value out, and then puts that data as a float. These are all floating point values into the body, and then moves on to the next one. If we don't get any information, then we're going to put it null. If we have GPS, I'm going to go and get the GPS position and then store that individually here into the message as columns in that list that we're filling up. Closing the list. Now we have added a row. And now if the data size of the body is exceeding the maximum payload size, which I set to, I believe, 1K or something. I could scroll up, but I don't want to confuse you now. So you can go with this, you can dial how often you flush. Or if the current RPM is 0, then we're going to go and force the message out, which means we're going to go and close the table, close the outer map, and then send the message out over to service bus. Now, this is it seems to be a little weird that as if we go to 0 RPM, we're going to flush it out. That's a trick that I'm using with my car specifically. My car turns off as you turn off the engine, that is usually a moment before the power goes out in the car. But it's not necessarily the same moment. So you can go and flush this out. If you run this in your own vehicle, what you may want to do is you may want to take a little battery, these rechargeable buffer batteries for cell phones, and put that between the Pi and your vehicle power outlet, so that the device will survive when the car turns the power off for several minutes. And these things are cheap. And then as the RPM drops to 0, which it does when the car is off, then you can go and flush out the last message and let the application live until you turn it off. Or this loop will obviously continue. So when you get back into the car while the battery still lasts, then it's going to power up again, and that particular drive is going to continue. And you could go and add some logic here to, if the car has been sitting there for a while, then we're going to create a new drive, etc. You could go and add that logic. And then here it's going to wait. This is a funky way to do waiting. I didn't touch this. And then once the loop is over, which is when the exit signal is received, then it's going to go and do a clean shutdown of stopping the messenger, close the serial port, etc., etc. So that is it. So what you see is I think the key port here is the key point. In addition to just sending a Qubit proton message, which is super easy from this device, is the encoding is when I go and create these telemetry messages, is that I create a map that contains 2 entries. One is a header section and one is a data section. The reason why I'm making this a map is that I could go and omit the headers because they're going to be the same all the time. And then just have the data and be able to distinguish that fact. For that, the map is nice. And you also see I'm being pretty greedy with names here. So H and D, and I'm keeping these names short because I don't want to make them too big and to have too much wire impact, because obviously that also goes on my data. So that's one nice way to go and encode telemetry, go and batch it. This is what I'm doing. So I'm not sending a message every time. I'm just batching it up in that one message. And then as I either reach a threshold or I see some urgency to flush the data out, then I'm actually going to flush it out. Doing that in this way will yield a fairly efficient implementation that is also greedy on the wire. And whether you want to go and include the headers or whether you want to make the backend clever, that really is up to you. So that's the, and then what you end up with is on the server side, you end up with a data stream. And we're going to take a look at that as well. The matching server code is in this Windows Azure project. It's in C#. Here I have a worker role. The queue name, I have hardware, and that's A6. I have the settings for the namespace configuration and the storage account configuration in config. And as I run this, I have an on message loop that's part of the client API for Service Bus. So this is now it's now pulling on a queue basically continuously until the completed event is set. And whenever a message comes in, it's calling process vehicle message. So before run is being called, we obviously set things up. Here on start, I'm taking the connection string from the settings. I'm appending the transport type AMQP, which switches the Service Bus API into AMQP modes. I'm setting up the cloud storage account also from the configuration to be able to go and store into stable storage. Create a namespace manager for Service Bus from the connection string. See whether the queue exists that they want to go and pull from. If not, then I'm going to create it. So this kind of, as I spin this up, it will create the queue so that the device can go and send to it. And now I'm creating this client that I've just referenced over with the onMessage from that connection string. And I initialize the storage writer, which is a little class that I have in here, with the storage account, which then is being seeded with the telemetry name for the two tables, telemetry and trips. Then further up, here's the process vehicle message. Here you see this separation that I just showed you in the C code. If the trip message comes in, then I'm going to go and call the process trip message on the storage writer. If the telemetry message comes in, I'm calling process telemetry message on the storage writer. And so on the storage, and this is kind of what's in this file, right? This is the worker role. So the storage writer, what that will do, it will take the trip message. It will get the body as an object, and this is where it kind of gets pretty dynamic here. If you use this AMQP encoding, as I showed you in C, you can go and very dynamically pull this out. Since we're creating, as we see an AMQP encoded message, we're creating dictionaries and we're creating arrays and values as you stuff them into AMQP. So the way to interact with AMQP encoded bodies is to get the body as an object and then go and treat it dynamically. So you get the trip info, and then we get out of the trip info the ID that we encoded, then we're going to go and take that, and this comes out as a GUID because we put it in as a GUID. It comes out as a GUID, and then we take the start date, and then we put that into the trip table. And for the telemetry message, we get the ID of the trip, and then here's the header section, here's the body section. So we go and take the timestamp, we convert the Unix timestamp to a datetime. That's a unique epoch that I'm converting here. The logic is right in here. Hang on. It's right here. So datetime into epoch to datetime, very simple. And then I go and create this dynamic table entity. That's something I'm using from the latest Windows Azure Storage API. Add the timestamp from row 0. And now I'm going effectively through the individual values, and I'm taking the fitting header for that column, and then I'm storing the column value into into the table as a dynamic entity, which means I don't need to know anything about the concrete format of the message. I'm basically just taking I'm assuming that the first column is going to be the timestamp, and then otherwise it's completely dynamic. So whatever I create on the pie, I will pass through here and just store into table storage as it is. And then I'm going to flush this out as a batch. So to make sure that I am doing this quickly enough. So this is very simple. AMQP messages, this is the one thing to keep in mind, is AMQP messages really come out as the maps and lists come out as maps and lists, as dictionaries of strings and objects and of lists of objects. And the best way to deal with those is to effectively make the message dynamic and then go and just iterate through it using the dynamic types in C#, which makes it very script-like. It's very nice to process those things. So with that, what you've seen is an example of using Apache Qpid Proton from a Raspberry Pi. Thank you for sticking with me through this episode and also through the past episodes of this series. With that, I'm going to declare that finished with 8 parts. I'm not going to be done with talking about devices, but I think I'm going to stop with the numbering. And the end of the year is actually a good opportunity to do this. So now we have this blog of Device to Cloud series with 8 episodes, which I think is a fairly nice round story from introducing you to a number of devices, and then leveraging the Arduino to kind of to talk about service-assisted connectivity, and then also showing you the Raspberry Pi as something that is not Windows, what we're used to as a more capable device in the Microsoft world, but something that's something like a device that's being used, for instance, in these telematic scenarios, as the Pi is in the car. Obviously, that's usually not a Pi, but that's a box that sits kind of behind your dashboard. But the technologies are surprisingly similar, and in fact, there are a number of engagements that we are helping with that are very similar in nature. If you have something similar, if you are doing telematics, if you're doing industrial automation, if you're doing medical devices in hospitals, any of those things, and you want to talk about that with us, you are cordially invited to either write me email to clemensv@microsoft.com. Mind that I'll be on vacation until January. Or you can go and contact your closest Microsoft office, or if you have a Microsoft Key Account Manager, then you can go and contact them as well and ask them to get in touch with us. What I'll be doing starting next year is I will be continuing doing this blog, and I'll be continuing talking about devices, but in more isolated episodes, talking about particular communication paths, talking about particular kinds of devices. We'll talk about microcontrollers. We'll keep talking about the general area, but I think this series kind of is one nice and round story arc. So we're going to close it kind of with this, and then go with individual episodes, which are talking about not so story arc related things, more in isolation in the next year. Until then, I wish you a great start into the new year, a great transition into the new year 2014. And if you celebrate the holidays, then I wish you very nice, peaceful holidays, good time, have a good time with your family. And I will see you, you will see me next year. Bye.